to start recording. And then the first sort of society that you hear, I didn't share that, so let me share it. Then the first society that you hear sort of after the Sumerians and stuff would be the Greeks. So the ancient Greeks were really known, and they're really known for their like geometric proofs. So let's look at ancient Greece. So they give us like a time period. Because Euclidean was the guy that wrote the book with all the axioms, and that was around 300 BC or 333, I think, somewhere around there. And then you had the Roman conquest of Greece, and so then they kind of took over stuff. You had the Library of Alexandria that got burnt down like several times. It was the largest library, so hopefully you've like at least like heard these words in another class before you came here. They're probably somewhat familiar, hopefully, but if not, I guess I get to be the first person to tell you about it. I don't know. So I believe it was Eudoxus. I believe it was. There's one of them that really like put an emphasis on deductive logic, and then you have people like Plato that really put an emphasis on this deductive logic sort of thing. I think he was the father of modern. Does it say that in there? And a lot of these people, like their works are lost, or like what we know of them is kind of sort of legend, and we don't really know like whether a lot of history was like sort of, was it legend or was it real? We don't really know. So these are the ancient Greeks. You have probably heard about a few of them, like Eudoxus. We've talked about Euclid, right? Euclid and his elements. There he is drawing something in the sand. Trying to remember which one it was. I think it might have been Euclid. There's an invading army, and he was like too busy with his circles in the sand. He told him to bug off. He didn't last too long after that, but the circles were really important. So there's Euclid that wrote like the book basically on geometry. There is Archimedes was a really popular one too. You probably heard Archimedes. So he did a lot of work, a lot of engineering and astronomy as well. I believe. Trying to remember who did what. There's a lot of Greeks, and it's trying to remember which name goes with which accomplishment is a bit of a. I need like a multiple choice or something, and I ain't got it. So there is a female. It starts with an H. Hypatia. Hypatia was a really popular female mathematician out of Alexandria. So there's a lot of sort of things happening out of Alexandria. So happening with each one of these sorts of movements, right? There's a sort of like city that's backing these intellectuals up every time, right? So there is a sort of like social thing that also goes along with these. And you have to have resources and those things of the sort to sort of like produce these things and have them written down and to have them there. It's not saying necessarily that other people didn't discover these things, but this is the sort of thing, this is the route through which we know our information, right? It's probably more accurate way to sort of describe it. So anybody have a favorite Greek I missed? There's Zeno with his paradox, if you want to know about paradoxes. And Zeno's paradoxes, he did one with Achilles and the turtle. He did one what was the other one? Achilles and the turtle, and there was a one with the firing of the arrow. And so these are really playing upon the mathematical principles and the mathematical principles of limits and things that they didn't really know about infinity at that time. So if you want to go look at his paradoxes, that's what it's playing with. You might need some like pre-cal or calculus to like kind of describe what's happening there. Where are we at time-wise? What about algebra itself?
Wasn't that like the Egyptians?
Okay, so
that-
Alexandria is in Egypt, right? Is what it said. So it's really kind of weird because like Alexandria is kind of the capital of Greece, which is across the river from it, but like it's in North Africa itself. So that was kind of weird itself. Is like the capital of Greece wasn't actually in Greece, or when Greece was the big sort of forefront. Algebra. So the prefix AL. Where does that prefix AL come from?
Alexandria, I guess.
Not Alexandria. If I'd say like Al Jazeera, I guess would be like a big
Okay.
one. Where's that Al coming from? Is he gonna come up? No. Okay. Okay. Let's see if I can do this. Muhammad Musa al-Khwarizmi is this guy's name. But this guy, if you read his last name, this I believe is where we get algorithm from. So don't ask me, but people can't speak very well, I guess is what the basis of this is. Al-Khwarizmi is the guy's name. Do they say the book in here? I'm trying to look at the book. His name given rhythm to algorithm, Spanish word in Portuguese, algoritmo. So there you go. His book, where's it at? The compendious book on calculation by completion and balancing. Does it say it in here? Right there. There's the word Aljabr. Algebra. That's it. So he wrote the book on algebra. And so there's always been this sort of like a society that's been sort of, what I want to say, like putting forth probably like the bulk of mathematics, I want to say. And it started with like, the Sumerians, it started with the Greeks, it started with, and then when the Greeks and all this happened, if you're looking at these dates, these probably coincide with when things like the Black Plague and things of that nature were happening in Europe. So they kind of lost some stance in what they were doing. And so these guys kind of picked up the Greeks' geometry, and then they started doing symbols to represent what they were doing with the pictures and the geometry. So you start doing things symbolically, you start doing that geometry symbolically, it becomes algebra, right? And so this is kind of where algebra gets derived, is in Baghdad was a big capital back then. So Baghdad was his big capital sort of city. If you think about the Baghdad battery and all that sort of stuff that was happening, there were a lot of advancements in society around Baghdad around this time. So the other thing we get from them is our numerals. The numerals that we use come from the Middle Eastern numerals, the 1, 2, 3, all these things you're seeing on the screen, right? All these numbers. What else? I'm trying to think of the areas that were next. Because it was like Sumerians, it was the Greeks, and then it was Middle Eastern. And then I want to say we're getting pretty close into it being like Austria and Germany. So for a while, Austria and Germany was really sort of a powerhouse until about the 1930s. And so if you want to go look up things like Bertrand Russell and David Hilbert and David Hume, and I'm trying to think of all of them, but they were really getting into, after they put things into like algebra and stuff, they started realizing this deductive logic and all this sort of stuff was really like something that could really build these fields of math. And so like David Hume and Hilbert and Russell and Wittgenstein was kind of an arch nemesis, buddy of Russell. So if you want to go look up these people,
Euler, Fermat.
Euler and Fermat, yeah, those would be good examples too. So I'm trying to think of the city too. Was it Berlin? I believe Berlin was the capital back then. I could be wrong. And so what they were trying to do is they were trying to axiomatize like the math systems. They were trying to come up with everything that you could come up with. And then there's this guy called Gödel, Godel. And he's got that little umlaut over his name. And he kind of proves that you trade consistency for completeness when you like create these systems, which is probably a whole nother, they teach entire classes over this concept. So if it sounds crazy, it absolutely is. And it probably requires a lot of preoccupation with these sorts of concepts just to think about them. But consistency means like you don't have two things that are contradicting. Completeness means that you do everything that you can possibly do. And so what he suggests is actually we can always create new axioms. If we want a system that doesn't contradict itself, we're always going to get new axioms that we can come up with. But there's always going to be some sort of rule that we can always just state and sort of prove. So he's known for his incompleteness theorem, and he kind of proved that like what they were trying to do is not going to really be possible, most likely. And I will say, like, even though that what they were doing isn't possible, a lot of the stuff they did is still super useful, right? And so that was what, Germany, 1930s. After that, I want to say it was like more Cambridge and Oxford kind of took the torch. I forgot my introduction there. So there was this bridge, or there was this river called the Cam River, and they kept going over it at a certain spot. So they built a bridge on it, and then they built a bridge then they built a college right next to that bridge. Guess what they called that college? They called it Cambridge. There was a ford river. There was an Ox River, and they used to ford the Ox River at a certain spot. They built a college at that spot where they forded the Ox River. Guess what they called that college?
I didn't know that. That's
They
interesting.
called it Oxford. I'm pretty sure. From what I've been told, I should probably research that more before I tell an entire class.
Good.
But
I believe it.
But that's what, yeah, I've had professors say that, so I tend to believe them.
You know, it's also really interesting is phi and the golden rectangle and all that goes into like the architecture and just nature. Everything is built around mathematics.
And so we had Oxford, we had Cambridge, that was what in England, and then now kind of sort of, I guess it's kind of us, the US, but that's kind of not, we don't really hold that hierarchy anymore. But the US did for the longest time hold a sort of hierarchy in higher education of sorts. And we did really kind of advance some of the things. What about the medals that we get? Do you know that one? They don't give out the Nobel Prize in math. Nobel Prize is for like applied fields. They give out something called the Fields Medal. And that's a little bit controversial because sometimes once people start getting the Fields Medal, they don't do quite as much work. So
Have you ever watched Good Will Hunting?
Yeah.
Yeah, I know. That's just a fun movie to watch because I always sit there and go, I don't think I understand that.
It's, well, to be honest, like I like the movie. It's a good movie, but like it's kind of funny because the proofs that he's doing aren't really like, I guess they're harder. They're hard
Yeah.
for someone that maybe has no formal education in math, but like
Uh-huh.
they're not really that hard.
Well, they look hard to me.
If you know the language, it's not doing all the if you know
Yeah.
the language, it's not all that hard.
Yeah.
It's not super complicated like number theory, or it's graph theory is what it is.
Yeah.
Yeah.
What I think is funny sometimes when they're trying to show, like a hard mathematics problem in a regular movie is they'll put like a squared plus b squared equals c squared on the board, and you're like, yeah, right. That's not a very complex math class. Anyway.
I know the Futurama and the Simpsons are really good at getting their math correct because a lot of those people are actually mathematicians.
Uh-huh. Oh, really? Yeah. Cool.
And the other one that I've heard is really good is The Ring. I know the original Ring, like the Ringu, like the Japanese version definitely has. I think the American version has legit math in it too, but they are actually ring structures because that's something that we study in math.
I mean, The Simpsons has to get their math right if they're going to predict the future like they do.
Yeah, this is true. Oh man. Oh, I don't know if y'all know James Randi, but he just recently passed away. He was a magician / he like uncovered people that were charlatans, basically, that were hoaxing people. But one of the things he did is he put in his wallet, today is going to be the day that I'm going to die, every day, and we'll just put that in his wallet. He's like, I'm going to be right one day, and I'm going to scare everyone. Okay. A squared equals 49. I know what you're going to tell me. And if you tell me that, oh boy, what are we missing here? This was the name of the game, pretty much, for this section. If a squared equals 49, a is equal to 7, or a is
-7.
Yeah. Or you can tell me, oh, you can just say plus or minus 7, right? Either way, like that's one way to write it. That's another way to write it. So this is the sort of name of the game for this section. So I don't think your problem is going to get much more simpler than this in this section. So if something squared is equal to something, we take the square root. Anytime we have a variable and we're taking a square root, must put a plus or minus. So if you watch my video, if you watch my lecture, you probably got annoyed by me saying plus or minus. I try to say
every each one, you always mentioned it.
Do what?
After every problem, you always mentioned it.
Yes. It's one of those things you'll forget if I don't say it. You'll probably forget if I say it. But
and people won't forget it anyway.
Yeah. Okay. 3 says r squared minus 24 equals. So what's my strategy to solving this if I want to do the square root property?
Yeah, 24. Where r squared equals 24.
Yeah, so the strategy is to take my square term by itself. I have to both sides.
Then take the square root of both.
I take the square root of both sides. So if I take the square root of, let me do it in red so we can see steps. I take the square root here. What should I do?
Well, r squared becomes r. Plus equals plus or minus. And then I just broke down 24 and came out to 2 square root of 4. Look, if you're gonna break it down, it goes 212, and then 16 is 26, and then you can get where I'm going.
24. That's how you're breaking down 24. Plus or minus, what is this? 2, 6, is that what you said?
Square root of 4.
This is the 2. This is square root of 6.
My bad. Yeah, I misread it. My bad.
I think you did everything. You wrote it down correctly. Everything.
Awesome.
Got to bring it down.
All right.
Are we on the same page, hopefully? So this sort of strategy is to get the square by itself. So the first one, they start off with the square by itself. The second one, the square is not by itself. So then we have to rearrange it, move it to the other side. Once we get the square by itself, we take a square root. Anytime we take a square root, we should always put a plus or minus. We put a plus or minus root 24. If you got this far, you would get probably most of it correct. But we should really do some simplifying on this square root. So we talked about how to simplify square roots in the square root section. This thing is square root of 4 is 2. Square root of 6 is not simplifiable. So there we go, square root of 6. And we have this thing. If you really wanted to write this out twice, I guess you could do minus 6 and a positive. There are two solutions there is what I'm trying to emphasize, which is kind of like what we should expect because we're starting out with square things, right? And square things should give us two solutions. Okay. 1, 2, where are we at? Number 11. X squared plus 25.
Yeah,
Oh, man. This is interesting. We had things that look like difference of squares before. What does this look like?
it's going to be negative, so when you square root it, it's going to have an I in it. But we follow the same formula.
Yeah. So we could factor difference of squares when we had something like this. We called it like sum of squares, and we said it was not factorable, right? So we couldn't really solve these things before. But now we know how to do the square root property. This is something we should be able to solve. So you kind of said it. I want to get my square term by itself as a strategy.
Right.
I have to do what?
Subtract 25.
You got to subtract 25.
So the x squared equals negative 25. And then you square root them both.
And I'm taking the square root.
X should be x equals positive or negative square root of 5i.
I'm trying to do this thing. If I take out the negative, it's going to be, what is that going to be?
The I.
The negative is going to be the I. And the other thing I have is a 25 here. So if I do root 25, what is that going to give me?
5.
5. Okay. Real
Real quick, Mr. Seavers, I already put the I after the 5, but what if we miswrote it the first time and put the I before the 5? Does it matter which side it goes on?
Plus or minus I5.
Yeah, like when I first wrote it, it didn't make sense. But I know there's a formula that says 5i first, after.
It like if I'm being honest, like if I were grading it and you said plus or minus I5 on this problem, I wouldn't make a big issue out of it. I would give you 100% credit. Like this is the same thing, but the thing that we do want to do is we do kind of want to keep it in like this order, A plus B.
There it is. Yeah, that's the one.
And so we do kind of want to write that coefficient before the I and kind of get in the habit of it. But like to me, that's not a big mistake.
It's not. It just looks funny. You know, it's not wrong. It just doesn't look. It doesn't look good, but it's not wrong.
I agree. All right. Thanks for clearing that up.
Because this is like our A here is kind of like a 0. We don't see a real part. So it looks like A plus BI.
And usually I like to put the I in front of a radical because then you don't get it confused as to whether it's under the radical or not. But when it's a whole number, usually it looks better if you put it behind a whole number. Or
Yeah, and I guess we're breaking this form when we put it in front of a radical, to be honest. And that's why the book does it the other way.
Yeah.
It's in this form.
But I'm with you. I like it in front of the radical.
Yeah.
Is in some mathematics classes, you're asked to identify the real part and the imaginary part, and so, or the real coefficient and the imaginary coefficient, and so that's why sometimes it's better to have it in front of the eye. But in this class, it doesn't matter.
Okay. Yeah, so in this entire chapter, I don't know how to say it. Well, I guess I do know how to say it. The strategy is to get the square by itself and plus or minus when you take a square root. Like if you can remember those two things and those two sort of strategies, you should do okay, probably at least.
Well, one thing I will say to be careful about, you only want to use the square root property if there is only one, if there's not two x's in the problem. If there's two x's, you just use regular factoring. If there's just one x squared term, that's when you use the square root property. But if you had like x squared plus 5x equals 0, you would not want to use the square root property. It wouldn't make any sense to do that.
Yeah, we have to do, well, we have a few examples like that. We would have to do completing the square on those, right? And I think these were completing the square example.
Well, I mean, some of them you can just factor out the x, like x squared plus 5x equals 0. You don't have to use the square root property. You can just factor out an x. But if it's just one squared, an x with the square on it, then you can use the square root property.
Okay. Yeah. If there's an x term, then there's just a constant to
Right.
like 5x equals 0. That's what you're saying. And we can
Yeah.
factor out a constant. So
Yeah, if you've got a second x in the problem, you never want to use the square root property. You either want to factor it or factor by grouping or whatever, or factor out of GCF. Like if you have x squared plus 5x plus whatever, 25, you would just, or whatever, x squared plus 10x plus 25, you would just factor it like regular.
Yeah, this would be x plus what? X plus 5, x plus 5, something like that.
Yeah. So the only time you want to use the square root property is if there is exactly one x squared term in the problem and no x.
Yeah, so there's either like an x squared or you could have like multiple terms, right?
Right.
Squared.
Yes.
But
But only one x in the problem.
X squared plus 63 equals 0. Okay, so what is my strategy here?
You're gonna subtract 63.
Let's subtract 63. Let's do the steps in red.
Nice, so you can take the square root of both.
The name of the game is I have to take a plus or minus.
X should equal plus or minus. Well, when you break it down to 63, your two numbers should be 3 and 7. So it would be 3i square root of 7. At least that's what I got.
That'll get you there. That negative thing on the square root to take care of as well, right? Okay, so it looks like a plus or minus. You said this looks like a 3, and then I and a root 7.
Oh, real quick, on my screen says my network bandwidth is low. I guess it's making the microphone all messed up, and the screens are all slowing down. So if it comes like an audible over here, I just want to let y'all know I'm having bad signal over here.
All right. Okay, anybody have any questions about the strategy, about how we're doing this thing? So the strategy is to get the x squared by itself Once you do that, we can take the square root property, but we have to get the square thing by itself first. Is this sort of setup?
Real quick, Mr. Shevers. I'm sorry, go ahead.
No, go ahead.
I was going to say, regarding the homework before we move forward, it says only do problems 1 through 37, but the printout goes all the way it extends from 75 to 93. So do we do those as well, or do we stick with the original numbers?
93, those are the completing the square problems that we're not technically doing anymore.
Okay.
I'll probably show you how to do like 1 or 2 of them, maybe, just so we can kind of see why they're doing it that. But they're
I just
not
wanted to double
for
check.
the test or anything, right? So that's probably what you're more concerned about at this point. Yeah.
As long as we got that straight.
We're basically doing the completing the square, and I'll kind of give it away. We're doing completing the square to get to the quadratic formula, basically. You have to use it
So yeah, that's all we're doing that.
when you derive. So we haven't, if you look in the notes, right, or in the syllabus, you could probably figure it out. But like we're leading up to it, like right before this test, and then the first thing we're doing when we're coming back from the test on, was it Thursday? Your test is on Wednesday, so I think we come back Thursday with the quadratic formula is what we're doing.
Always a climax.
Yeah, so that's kind of the boy we're building up to. And so we're doing this, and we're doing this, completing this, or not completing the square. We're doing the square root principle. And I kind of said it, get the square by itself, then you take the square root. Cleaning up square roots, so we did that section about cleaning up square roots right before this. So this is my 3, this is my I, this is my root 7 stays root 7. So being able to clean up square roots, and we have said this, and we don't say these things just for fun. Like this class is going to build on itself, right? We have the square roots. Now we're doing the square root property. We're going to employ those square root properties within here, right? Same thing when we do completing the square. We're going to use all the stuff we know about square roots. When we go and try to figure out what the quadratic formula is, we're going to use the stuff that we know about completing the square. And then we should be able to solve just about any sort of quadratic formula I can throw at you. So right now, these solutions look kind of specific, if I'm being honest. We are getting into imaginary, we are getting into things that look irrational. So we are building the sort of solution set that we could possibly have. But these things have to look a very certain way, right? They have to look like just the x squared. There's no x here, and we get it by itself, right? They have to look a very certain way for us to be able to solve them at this point. We want to be able to solve anything and everything that's out there. That's kind of our goal. And so we get a few more. U minus 6 squared equals 64. So if you see this, you look at this and you
2 equations.
Is that happening here? Is this square by itself on this one? Is what you're asking yourself.
But can't you just square root that and just take that 2 off of it? Because you could just square 64, which it would make it 8.
That I think you're answering exactly what I'm kind of asking. This thing is being squared, right? And so if you have to, you can kind of just put your thumb over it. It is multiple terms, but it is being squared. So this is one thing. I know it's multiple things, but we can kind of look at it as one thing in the parentheses, right? And so I'm saying something squared equals 64. Or I see thumb squared equals 64, I guess is what this equation is telling me, right? And so hopefully this looks a lot like number one, right? We're back at that thing. We have our thing. It is being squared. I think the thing that like this might throw people off is that we have multiple things in our square, right? And so sometimes people see this and they want to move this around and they want to do something here. Look at your square and look at what is being squared. So this entire thing is being squared. This is my square term. It is by itself. And like Michael was saying, we take the square root of both sides. And if you take a square root, what should you do? Always.
Plus or
So
minus.
minus.
Oh, there's that enthusiasm for the thing I've said a million times. Plus or minus. What is that left side? Maybe I should say it like we definitely want to put the plus or minus on this side, not this side, right? Put it on the number, not on the crazy variable thing. What is this thing when I square root it?
U minus 6.
U minus 6. Sometimes people mess up when they try to square root that. There's a lot of numbers and symbols there. But this square root, sorry, this square are combinations of this thing and that thing. Things are undoing each other. So that's the U minus 6. This is plus or minus root 64. You're probably telling me hurry up and fix that thing. So this is like U minus 6 equals plus or minus root 64 is
8.
8. If you got this, you would be almost there. You didn't quite solve it yet. So what do we need to do? And if I'm being
U by
honest,
itself.
I might write this, I might split it up at this point. It might be easier. So this is what you might into. There's two things here I'm trying to write. What are those two things?
Well, it looks like it would be like U equals positive 14 or U equals negative 2.
Oh, yeah. I think you're doing way too much work. Either it's a minus 8 or it's a positive 8, is what we're saying, right?
Oh, okay.
I think that's what I'm hearing. Is that what you did?
Yeah, so we would keep
Yeah.
it like that?
No.
Oh,
You want to keep it. I was just making sure everyone is on the same page because you're doing like 2 or 3 steps, I think. Making sure everyone can see where you're getting those numbers from. So minus 2 or U is equal to or 2 minus 12. So I would probably split them up. You don't have to split them up, but I would probably split them up. You could try to add 6 here, but you're going to try to add 6 to a positive 8 would give you this. You're going to add 6 to a negative 8 would give you that. But that's a lot of work to do in your head. And I would not chance that. It is really better to write these things out. If they're going to look the same, I would probably keep it as plus or minus, if I'm being honest. If it was like the same thing like that, I would keep it if it's like 3 plus or minus. But these are actually giving you 2 different numbers. So the second I realize I'm going to be crunching things and they're going to end up different numbers, I'm going to split it up. At least that's just my sort of general approach, I think. It's like I'm doing different things. I should probably write them out differently, right? I highly suggest splitting them up when you get to that point. Does everyone see sort of how we're doing this thing? So we get the square by itself. We take a square root. And the name of the game is anytime you take a square root, you better plus or minus. If you do plus or minus, if you don't, you're only going to get half your solution. You're only going to get the positive half. We need the other half. You're going to only get half credit probably for that problem. You're only showing me half the solution. Got to get that other half. Got to get that negative half. And again, this is coming from the fact that when we square things, we can square a negative thing and we can get a positive back, right? So this 125, I'm going to give you like 2 or 3 minutes to do this by yourself, because like after we did 23, I feel like you should definitely be able to do 25. It was a little bit harder, not a lot. M minus 6 squared equals 20. I'm going to give you almost a few. Okay. I think it's probably a pretty good amount of time. M minus 6 squared equals 20. So like the first thing you want to ask yourself, is the thing that's being squared, is that by itself? So if I look at the thing being squared, it looks like all this stuff in the parentheses. So the thing I'm looking at is there's nothing being added like out here. There's nothing being multiplied like over here, right? That's what I'm talking about. Is it by itself? So there's nothing like added. There's nothing being multiplied. This thing is just something squared by itself, which hopefully you notice because it looks almost exactly like 23, right? And so that's the first thing I asked myself there. The first thing I did was I took a square root of both sides. And anytime I take the square root of both sides, I always got to take plus or minus. So if I do m minus 6 to be this side, this is equal to plus or minus root 20. So there's a little bit of cleaning up I got to do with this root 20. I think I can split this into 4 and 5. And if I do root 4, this should give me 2. This should give me square root of 5. So even if I want to put maybe square root of show you. All right. Did you get this far? Hopefully. Now we're here. And there's probably a sort of way I'm going to write this just because it keeps things cleaner for where we're going to go. And this is just kind of out of foresight. I want to add that 6 over. And this is kind of the sort of thing where I said, like, if it looks all the same, I'm probably going to keep it together. If not, I'm probably going to separate it. But I want to add 6 to this. So I'm going to put that 6 out in front. If you really wanted to, you could put it out over here. You could go plus or minus 2 root 5 plus 6. That would be correct. But I really want it out in front, and this is just kind of sort of like it's by what do I want to say? I have a little bit of foresight knowing where we're going to go, and it's kind of one of those things that's by convention, right? It looks prettier that way. Now, if I want to split this up, I can split this up. I have one that looks like 6 plus 2 root 5. I want that looks like 6 minus 2 root 5. So write it kind of one way or the other. I don't really need both ways. Just kind of figure out one way. But now we're looking at this. Can I simplify this anymore? That's probably the next question that pops into your head, or hopefully should be. Can I do that 6 plus 2 or that 6 minus 2? Oh.
No, because the 2 is attached to the square root of 5.
Yes, that's what I want you to look at. This has square root of 5 on it. This has nothing. So this goes back to the like terms, right? If this has a square root of 5 attached to it, if this had a square root of 5, we would say these are like terms, we could add them, right? But these don't. So maybe going back, if we had something like this, we could absolutely combine it. So maybe picture. So if they both had a square root of 5, we absolutely could combine them. But since one does and one doesn't, these are not like terms. We can't just go combining them willy-nilly like, right? Okay. So this is it. That's a little bit tangential, right? But this is it. Questions? Heavy size? Anything? Yeah. So sometimes knowing where to stop is a good thing to do. All right. So we got 2 more. 5c plus 1 squared equals a minus 27, and 4x minus 3 squared plus 11 equals a minus 17. So 30, what is this, 35? 35 looks pretty similar to the stuff we've been doing. They just up it a little bit, right? Okay. So what's the first thing you should do if it's not done for you? You want to get what by itself? I might have to do 2 fingers. You want to get this thing by itself. So whatever the heck is being squared, you want to get it by itself. Is that done for you on this one? Yeah. So that's already done. So once you get the square by itself, what's the next step?
Both sides.
Yeah, the name of the game is square root property, and we use the square root. We use the square root, and anytime we use the square root, always got a plus or minus. If I take a square root of this left side over here,
Becomes I at 5c plus 1.
5c plus 1, and this is equal to plus or minus. 27 is what, 9 and 3, I think is what I'm going to do.
Well, I got 3i over 3.
3i, is that what you said?
Yeah, 3i square root of 3.
Yes, square root of 3. I thought you said 3i over 3. I got scared for a second. Okay. That's absolutely what it is. If you want to break this thing apart, I guess I'll do it real quick.
It's tricky.
27 into 9 into 3. Square root of 27 into 9 and 3. This is 3 with the square root of 3. You want to simplify it. So I know I did that pretty quick. And the other thing is it had a negative, right? That's our I.
I keep forgetting if it's to put the I inside or outside, but
I definitely goes outside the square root.
yeah, I had to double check on other paperwork just to make sure.
Yeah, and it's a weird thing, but the square root of I, right? And we won't go too much into it, but this is not the same thing as I. It is actually different. It's more complicated, and we don't want to talk about it. We don't want to talk about it. It's too complicated. Okay.
Matt?
Yes.
Oh, okay, so I was looking at their homework assignment and I was wondering if, because I know on the test, there's a couple of problems that I want them to be able to see. They're not really hard, but on their homework tonight, 2 of the problems are completing the square. So they're number 3 and 4 are completing the square on the written. So they need to cross those out. And then could you give them?
All I have is these 2. I don't have 3 and 4 on mine.
Oh, you don't have 3 and 4. Oh,
yeah,
okay.
that's all I got is in 2. Those 2
Okay.
They should
Well,
be
can you give them a couple of examples just for grins, then, or at least one more? I just wanted to show them one more example because this kind of will be on the test because I know because I wrote the test.
Like this?
Not that one. No. Let me call it out to you.
Okay. What do you?
It's negative 16 times parentheses t plus 5 quantity squared plus 160 equals 0.
Okay. All right, we'll do that one after this one.
Okay.
Okay, so we have this thing. So this thing, they made it just like a little bit maybe tougher. What is the next step I'm doing to solve? So again, I know it has eyes in it, but what we're really trying to focus on is this guy right here.
I don't even know what's correct. What I did, I just subtracted it and I put it on the left side and I left it out there, but I left it as part of the equation.
What do you think? You subtracted it? Is that what you said?
Yeah, subtract it.
So you subtract 1.
Yeah. 3i root of 3 minus 1.
Minus 1 plus or minus 3i radical 3. And we want to get c by itself, so what are we doing?
Again, I don't even know if this is right, but I just divided it by 5 and left it at that. I didn't get an answer. I just put a 5 underneath it.
Yeah, that's it.
Seriously?
That's it. Minus 1 plus or minus 3i radical 3. Now there is one sort of thing you might want to do to check.
There it is.
You really can't do it here because none of these things have any kind of common factor. 1, 3, and 5 aren't going to have any common factors. So there's really no simplifying you can do. But if you want to check, you could look at maybe a -1. You could write them out like separately under that common denominator, right? So sometimes this might be a step we might want to start heading in for some reason. But to me, this is a solution. Like if you got that far, that's as simplified and clean as that thing is going to get. I could write them out twice as well. I have a -1/5 plus 3i radical 3/5 and something like -1/5 minus 3i radical 3/5, right? There's one that's plus, there's one that's minus. The reason why I'm kind of splitting it is sometimes you might have something that can simplify. Like I know this is -1/5, we're not gonna be able to simplify that. 3/5, we won't be able to simplify it. But something like 3/6 we would, right? So sometimes separating it helps you to see how to simplify it. Because I think we went over that again, right? If we simplify it, it's got to come out of everything. Sometimes people try to simplify things wrong at that step. Okay, so this one. So if we want to solve something like this, what is the first step? I feel like this is more difficult than that. 37.
No clue.
So we want to use the square root principle. So we want to get what by itself?
The square.
The square. So what is being squared? That's what you need to look at. This thing is being squared. T plus 5 squared. Okay, so I need to get everything that's not the thing I just underlined to the other side. So how am I going to do that?
Just addition and subtraction.
Yeah, so I subtract what? 160, I think. I get a -50 plus 5 squared on one side. I get a -160 on the other.
Oh, you mean positive, right? Oh, no, it's negative. Okay.
All right, so what goes on next?
Divide by -16.
Got to divide by a -16. So divide by -16. If I divide that side by -16, I'm going to get my t plus 5 squared that I want to. If I divide this by -16, I'm going to get a +10. Okay. So now I see something like this, t plus 5 squared equals 10. And I said the first step I want to do is to get my square by itself. And then what do I do?
Take a square root from both sides.
So now it is ready for the square root. So I can take a square root of both sides and
Plus or minus on the right side.
Oh, yep, there it is. Okay, so this left side is going to look like what now?
T plus 5.
T plus 5, and this right side looks like plus or
Plus or minus square root of 10.
root 10. And if we think about root 10, I can think about 2 and 5. And if I take a square root of 2, take a square root of 5, none of that's simplifying. So we can't really simplify this. And in general, if we can get primes out of things, right? 2 and 5 are what's into 10. I'm not going to get 2 of the same thing there. Numbers on the page at one time. So 2 plus 5 equals plus or minus root 10. What's the next thing I want to do?
Subtract the 5.
I'm going to subtract the 5. So I subtract 5. Subtract 5. I'm going to leave the thing I just subtracted. Plus or minus. Okay, minus 5 plus or minus root 10. And so there are 2 solutions here. And so if they wanted it like that, that would be fine. But if they wanted an approximation, then you're going to need a calculator, right? I guess. But if they wanted an approximation, we could also give them an approximation for this thing. Which sometimes when we get further, it might be worth noting like what the approximation is. So I think minus 1.84 is what happens if we round it there. 0.116. So like these are all fine and well, and these are the things we actually prefer, right? So these are actually the things I would probably prefer, or definitely do prefer. But sometimes, you know, like if you're graphing something, we need the approximation to make sure our graph looks correct, right? So I think we got one more problem that is on the agenda for today. And I think it might even be simpler than the last one we did. We get 4x minus 3 squared plus 11 equals minus 17. And again, I want to look at the thing that is being squared. So the thing that I see with a squared on it is this thing right here. If there's any number out here, which there's not, right? We would have to account for that somehow, right? Like we did in the previous problem. So if I want to get this by itself, what is the first thing I should do?
Subtract 11.
Subtract 11. So if I subtract 11, what does that give me? Minus 28? And what's my next step?
Take a square root from both sides.
I have my square by itself. I can take the square root from both sides. This side is going to look like what? 4x minus 3 now? Squared. This side is going to look like plus or minus root minus 28. Okay. So this thing I can clean up. I think it's what, 4 and 7. I think are probably good numbers to break that up into. So the comes out. There should be a 7. And what else should I pull out of that thing?
An I.
Pull the I out. Pluck out the minus. Plus or minus. We talked about how to simplify square roots before. But this thing should simplify to 2i radical 7. This is still equal to 4x minus 3 And the name of the game is to solve for this variable. So don't lose track of where we are. But we want to solve for that thing. So if we want to solve for an x, I know this looks crazy complicated, but just look at this thing over here. So if you were to solve this thing for x, what's the first step you would do? If this is 4, yeah, if this is 4x minus 3, the first thing we're doing is adding 3. So 4x is what's going to be left on this side. If I add 3, this looks like 3 plus or minus 2i radical 7. And I know this thing looks crazy over here, but if you just ignored this and you just said I have 4x is equal to something, how do I solve for x? The next step is going to be to divide by 4. 4x divided by 4 is going to give me x. I have this thing 3 plus or minus 2i radical 7. And this is all being divided by 4. And if you did this, this is fine. But if we do break this thing up, so if we have 3 over 4 plus or minus I radical 7 over 4. So I'm not sure what Ms. Watson's looking for. But if you gave me this, I would give you 100% credit if it was me grading this one.
Yep.
Okay, so she says yes as well. So I think if you get that far, you're safe. But if you wanted just to look at this, you could actually simplify this a little bit more. The 2 over 4. This is I radical 7 over 2. And again, there's kind of a reason why I'm heading in this direction of splitting it apart. Notice this looks a little bit more like our a plus bi form when we start splitting it apart. With that said, if you got that far, I would be completely happy. Like, that is good enough. I don't really see that this is a lot easier to plug into a calculator and figure out than this thing, right? They look both about equally as ugly to me. Okay. So these things, you might notice, they either had just like a solo sort of square term happening, or they had these like perfect squares happening, right? And with nothing else happening. So if we have something that just a square by itself, or it's like a perfect square by itself with no other variable, we should be able to solve these things, is what this is kind of telling me. Well, guess what? Not everything looks like it has just a square or just a perfect square. Things look like other things. And so, again, this isn't really something you're requiring for this course, but it is something we're going to go over sort of briefly. So if it looks like other things, we want to make it look like squares. So the way that we do that is we make it look like a perfect square. So if we have something u squared plus 2u, I'm focusing just on these two things. So the first thing with a perfect square is that I have my square term and I have my variable term on one side. I take my b, which is 2, and divide it by 2. So I think the thing I need to add to this is like 1 squared, which is going to look like 1. So if I add 1 to both sides of this, I'm grabbing a shoemaker. If I add 1 to both sides of this equation, I have u squared plus 2u. Add 1 to that, it's going to look like u squared plus 2u plus 1. The thing that most people forget, and the thing that I will probably horribly forget if I don't spell it out, is I have to do 3 plus 1. 4. So a lot of people will forget to do it to both sides. But after I do that, if I added the magic number correctly, this thing should be a perfect square. One square. And if you want to do some like distribution to backwards do this thing and prove it to yourself. But now I have something that looks like u plus 1 squared equal to 4. And this looks exactly like the problems that we've been doing all day today, hopefully. I take a square root of both sides, and I can get it. So I take a plus or minus square root. Plus 1 equals what? Plus or minus 2. So when I subtract 1, I have a minus 1, minus 2, and I have a minus 1 plus 2 are my two solutions. So it's either minus 3 or a positive 1, I believe.
Matt, before we let them go, can you let me share my screen for just a minute? Because I want to show them something. I'll show them this tomorrow too, but I just wanted to show them something.
Sure. So I think that's it. The rest of them are just completing the square. So this is basically the same approach. We do 6 divided by 2 and square it, and we add it to both sides, and it will make a perfect square. I think this is pretty much set up the same. This you have to do some rearranging. So they're like trying to be tricky. You move the 10x to the other side, you move the 5 to the other side. So you do have to arrange things so that they're in the right order. But again, we're not going to go over that. So Ms. Watson, if you want to take it away, I guess you can go ahead or remove my pen. So we'll record what you're doing. All right, that's it.
Okay, I just wanted to show y'all one thing. Because this will be on the test, and I'll talk about it tomorrow too. It's totally what Matt's been doing, but it's in an applied problem. So let's see if I can get myself to share the screen.
Oh, is it vertex form? Because vertex form is like set up almost perfectly to do square root properties.
Exactly. Can y'all see my screen?
Yeah.
Okay, so this is what there'll be a problem like this on the test, and I'm hoping everyone will recognize that we haven't talked about it a couple days, that it's vertex form.
I'm not seeing your screen.
Oh, you're not? Oh, let me see if I can share it. Sorry. I can't, it's not letting me, oh wait, yeah, it is. Sorry, okay. Can y'all see it now?
Now we see it.
Okay, so there'll be a problem. It's an application problem, but it should be super, super easy. Because if you know the vertex form, what's the vertex of this parabola? Do y'all remember?
Is it -1 and 400?
Not -1.
Oh, 1,
Yes.
400.
Remember, this is the vertex form of a parabola. We'll talk about this in the review tomorrow, and I'm hoping y'all have already looked at the reviews for the test. So the vertex here, if this is vertex form, so the vertex is going to be 1, 400. So that means since t is the time in seconds and h is the height that we're getting to, that means that the parabola is going to reach its maximum height after 1 second. And that, how high will it go?
400 feet.
400 feet. There's a question just like this, guys, on the test. So if you know vertex form and I ask you, how high does the object go and how long does it take to get there? It's 1 second, 400 feet, right? So just pull it out. The one I wanted to show you that totally goes along with what Matt was teaching today is I'll ask you, when does it hit the ground? At what time does it hit the ground? So if it's hitting the ground right here, how high is it off the ground when it hits the ground? What's the height?
It's the x-intercept, so y = 0.
That's right. It'll be 0 feet. So what are you going to have to do to this equation to find out the time?
You would take a 0 and make the ht into a 0.
That's right. You're going to set negative 16 times t minus 1 squared plus 400
Equals
equal
0.
to 0, right? Just what Michael just said. You're trying to find the t. So you're going to set the whole thing equal to a height of 0. Does that make sense?
Mhm.
And then you're going to solve it just like we did with Matt. You're going to subtract 400 from both sides. Divide both sides by negative 16. What is that? 25. Take the square root of both sides.
Be sure to plus or minus. No.
And then you're going to have t equals to 1 plus or minus 5, right? Because you'd add 1 to both sides, which is the same thing as t equals 1 plus 5, or t equals to 1 minus 5. Now we're talking about a time. So here I'm going to get t equals 6, and here I'm going to get t equals negative 4. Which one would I throw out if we're talking about time?
Negative 4 because it
Right, because
doesn't
we're not
exist.
going back to the future.
Right.
And so what's the final answer going to be? If I
6
ask
seconds.
you 6 seconds, right? And we'll talk about this again tomorrow. It should be a lot. The reason that I'm a little concerned about it is because it is a word problem, which always freaks people out. But it's not, if you understand what a vertex form is, if you understand, you can just pull the vertex straight out of the formula. And then all you have to do to find the height with the time it takes to hit the ground is set it equal to 0, and then use the square root properties. Then you're good.
It should be like a little bit above the y-axis or whatever. It shouldn't be going through the origin.
No, you're right.
It might help.
Yeah,
Yeah.
right. Because yeah, exactly. Right. It's not, it doesn't start at the
And
origin.
so on the right side, we're getting 1, 0, and on the left side,
Right.
like a minus 4, 0.
Right.
Okay.
Yeah. Whatever. Anyway, that's horrible. But that's not even where that goes. Anyway, it goes somewhere like here.
But it could be going through the origin if it says they start off.
Oh yeah, it could be.
If they
but
start off from the ground, then it's going through the origin, right? But if we start off from some certain height, we're going to be going off of some
right.
certain height.
So like if you had yeah, anyway, it could be going through the origin, but it's not in this case. The rocket starts somewhere other than the origin. We don't really know where it starts. Here's a good question. How could we figure out where it starts? Could anyone tell me how you could figure out where it starts, what this point right here is?
That would be the y-intercept.
That's right.
Let's see.
So if this point right here is the point 6 seconds, 0 feet, what would this point right here represent?
Wouldn't you
Oh,
just put
That
zero?
would be
What?
0 seconds.
0 seconds, and what we're trying to find out is how
So
many.
t would equal 0 then, wouldn't
That
it?
is right, right.
So
good.
now you just plug in 0 for t,
That's right.
and then you solve it. Okay.
So
Right.
minus 1 squared would be 1.
Mhm.
So you can see where, quadratic functions are so applicable. Really, they are. You see them all the time because it's projectile motion. Okay, that's all I got for today. Tomorrow we'll have some fun going over all this stuff.
Yeah. Thank you.
Thank you.